In this video, I hope to bridge the gap between the understanding of the signal response stability versus the Bibo stability, and how this actually affects what we're gonna see in the next few videos, and also how we link the previous parts of the old videos to the subsequent ones. Alright, before I go into the Z domain, alright, I'll just start off with the S domain, because this is something that can use to convey the meaning behind what we are doing in the Z domain. Alright, so if you still remember, your transfer function is some G of S is equals to Y of S over U of S, your output over input, and do not be confused by your Z transform, which is this one is your Z output versus your Z input. Alright, so the notations are kind of like complex, confusing, but just take note that this is for S, and then that is for, just now what I did was, this one is the Z domain, the output versus the input. So this is output for Z domain, this is input for S domain. Alright, so be very careful. Now, we have a transfer function over here, S plus 1 over S plus 2. Alright, if I were to bring my input to the other side, what I have is this one over here. Right? So by itself, our transfer function is kind of stable, right? S plus 1 over S plus 2. And if you just check it out, it's actually kind of stable, right? When I plot the Nyquist plot of this. Alright, you did it. The minus 1 is over here, right? The minus 1 is over here, as you can see. So the Nyquist plot actually didn't encircle, right? So it's kind of stable. And in fact, it's so simple that it's just stable. Alright, but if we have an input, alright, input of a impulse response, which is 1, if you still remember. Alright, so therefore, if you were to do that, what do I have? For using this Nyquist plot, alright, I can actually go to the MATLAB and go to impulse. You can see the graph itself is kind of stable, right? You may say that it is rising, but at this particular point it's stable constantly, alright? It's just something like that, and all the way constant, alright? And therefore this is somewhat stable. So what if we input, instead of 1, we input a step function, 1 over S? What can we see? So just simply change to step, and you can see the response actually dies down, right? With this curvature that's going down, it's pretty nice. Alright, so what are all this? Alright, if you were to go in terms of, so these are all the responses that we have just plotted out, right? Just a while ago. I don't know where am I now. Yeah, anyway, this is somewhat of the responses that we have plotted, given that we have instead of input is a step input 1 over S. These are all the step responses. Alright, therefore what is actually the Bibo stability? Alright, is that the input itself is, let's say, our transfer function. Alright, our input is 1 over S, which is this graph over here. Pretty stable, so it's a bounded input because it didn't go to infinity. Infinity then is unbounded, right? And you multiply, or you convolution with your transfer function. The transfer function, if just now when we put in our impulse, is actually going this way, right? Alright, this is the pure transfer function itself. Alright, so therefore when you multiply, convolution them together is equals to this one over here. And you see, this is actually a bounded output because you didn't went to infinity. You didn't sprung out and go to infinity. You just died out and eventually become very stable. So therefore, this is bounded input. Alright, go through the transfer function, becomes a bounded output. Alright, straightforward for the S-plane. Alright, for the Laplace domain, or the, yeah. Now, playlist of l4v1 and l4v3, if you were to watch that video, will actually prove to you that this particular stuff over here is kind of stable, alright? And these are all the responses. Alright, you may wonder in the past why are all these U's. If in the Z domain, the U or UZ, or simply the U itself, is considered the output. Alright, while the E itself is considered the input. Alright, and what we are plotting over here, alright, is in fact the response of the output. Alright, it's simply just straight away plotting this thing. Alright, with a certain form where we can sum up the responses. Alright, we take the responses with the time step k minus 1 in relationships to the time step of k minus 2. Alright, this is one way to actually sum up your responses to get your signal response, if given that you have no so-called transfer function. Alright, so as you can see, this is all in terms of the output. Alright, these are all in terms of the output. Alright, as all this example we have done earlier, right, these are all in terms of the output signals. Okay, and therefore for such of the case, if you were to work it out, things like that, you'll get a characteristic equation of some equation, right? And then you solve for your z, eventually you know that it's stable. Alright, we can call this the bounded output. Alright, because it's going towards stability, it didn't went infinity, right? So it's bounded output. But we have no understanding of whether is it a bounded input, because over here there is no input at all. These are all outputs in terms of outputs, and therefore after which they compute all the outputs and have this thing over here. This is what we have discussed in our L2v2 and L3v2 and L3v3 videos. Alright, in the next subsequent videos, alright, we're gonna prove in terms of the somewhat a transfer function type of thing. Alright, some s plus 1 and s plus 2, but instead of s plus 1 and s plus 2, if you remember in our previous videos, I mean it's our l4v1 video, you can actually watch it. We actually derive the transfer function for the z domain. It doesn't rings a bell, it's actually this one. Alright, we derive all the way from something like this. Alright, and where is this coming from? It's actually coming from the integration. Alright, the integration formula, taking this is the trapezoid input. Alright, you're gonna input it into the system and somewhat deal with the previous output and get your outputs, current output or whatever, as we said earlier. So these are the relationship between the output and the input now, right? Output and input currently. And if you were to compare with just now what we are saying, these are all the outputs only, alright? These are all u's. If you were to just explicitly define over here, these are all u is equals to your output. Alright, E is in terms of input, so therefore this equation is in terms of output and input, and therefore what you have will be your so-called your transfer function that we derive through all these little steps. Alright, going back to this one, signal response stability versus the Bibo stability, we could highly suggest that this is actually a bounded output stability only. We don't know what is the bounded input signal. Alright, and in fact we have already done the bounded output already. That's what all of this is being here, but we aren't actually given, alright, the transfer function itself. It's like you are given C, alright, and then you are asked to derive and compute C, alright, but you don't know what is C made of. It is made of A plus B. Alright, and therefore this A plus B is gonna be discussed in the subsequent videos that we're gonna come. Alright, so currently what I've been doing are all just some things about the response. We don't know what makes up the response. Alright, and what makes it totally Bibo stability. Alright, and because dealing with the inputs is kind of like yeah. Therefore in the next subsequent videos we'll talk about the transfer function back, alright, in a more detailed way. And then if you rearrange this input, you just bring it over here. Alright, it's just this thing over here. It's in terms of your transfer function, and your input equals to your output. Alright, and we will first start off with talking about the input. Alright, EZ. Okay, we'll start off by talking about this input in the next subsequent videos. And I shall see you there.